Good morning, children. Today we will discuss about mode locking in latches. Mode locking in latches. Let us go with the presentation. So let us see the mode locking in latches. What is mode locking? So here it is a technique that we have to make the laser to produce the extremely short optical pulses. That means 10 power minus 12 seconds or 10 power minus 15 seconds of high peak power. That means within a short period of time, picoseconds or femtoseconds, we have to make the laser to produce a very high peak power within a short period of time. So here, to understand the concept of the mode locking, here we will consider a laser which is formed by a pair of mirrors. That means already we have an idea that laser can be formed by a pair of mirrors which are separated by a distance d, enclosing the active medium. So with a line with delta nu about a central frequency mu naught. Already we will see in the figure. So as we have discussed earlier, the frequency spacing of the longitudinal modes of the resonator is C by 2D. Already we have discussed about this. Longitudinal modes of the resonator, the frequency spacing of the longitudinal modes of the resonator is C by 2D. So hence, if the laser medium is able to provide a net gain over a bandwidth delta nu, then the laser would oscillate in a number of frequencies. That means here, let us see it here. So this is the gain profile of the active medium. So centered at a frequency nu naught. So this is the frequency here centered. It is the frequency of nu naught, and the bandwidth, the line width or bandwidth here delta nu. So here the line width is delta nu. So the longitudinal mode separation is delta nu, which is equals to C by 2D. So here this is the gain curve, and here the line, this is the loss line, and here we can see delta nu equals to C by 2D. So here let us see. So here the laser would oscillate in a number of frequencies. So we can observe the laser can oscillate in a number of frequencies separated by C by 2D, and the actual number of oscillating modes would be. Now let us consider the actual number of oscillating modes. Already we have an idea that the laser can produce number of modes. So here the actual number of oscillating modes would be n plus 1 is equals to 1 plus integer which is closest to the delta nu by CD, but it should be less. That means here n should be here, which is close to the delta nu by CD, but it should be less than this much value. So here where we have assumed that there is a mode at the center of the line, we have to assume a mode is at the center of the line. So the total output from the laser can be written as, how can we obtain the total output? By the superposition of the fields of all the modes, we will obtain the output. So total output can be written as E z comma t, which is equals to sigma m equals to minus n by 2 to n by 2 an exponential minus I 2 pi nu n t minus z by c plus I into phi n. So this is the equation number 2. So here an, which represents the amplitude. Here n is represents the amplitude corresponding to the nth mode. So here in the suffix we have n, which corresponds to the nth mode, and here phi n is a phase. So in general, amplitudes of the various modes are defined by the gain available at the various frequencies and are determined by the gain profile of the medium. So on the other hand, phases phi n of the various modes are arbitrary. So for such a case, output laser intensity. So here, laser output intensity proportional to the mod E z comma t whole square. So which is given as I of t. Here I is intensity at a particular time t. So intensity can be given as K mod E of t whole square. So K, here E of t, already we have some fields here. So E of t, so sigma n equals to minus n by 2 to n by 2 an mod an square plus k into sigma n, which is not equals to m, sigma m am asterisk. So into exponential minus I 2 pi v nu n minus nu m t minus z by c plus I phi of n minus phi of m. So here this is the output laser intensity, which is proportional to E of z of t whole square. So here what is K? K represents the proportionality constant here. So for the arbitrary values of the amplitudes and phases of the various modes, the above expression represents, so this expression represents a fluctuating output intensity of the laser. This equation represents the fluctuating output intensity of the laser, so which can be seen here. So this is the fluctuating output, so which is shown in the figure 6.10. So here, so it can be verified from the equation. So by verifying this equation, we'll obtain I of t is equals to intensity is equals to I of t plus 1 by delta nu, which is equation number 4. So where delta nu is equals to c by 2t, which represents the intermodal spacing. Intermodal spacing. So thus the intensity pattern repeats itself with a periodicity delta nu. So even when the modes are uncorrected, correlated, so at the same time from equation 3 it follows that within these quasi-periodic intensity fluctuations, the shortest fluctuation occurs in the time of the order of the frequency difference between two extreme modes, and which is given as TF. Intensity fluctuations. So here TF represents the intensity fluctuations. TF is equals to nu naught plus 1 by 2 n delta nu minus nu naught plus 1 by 2 n delta nu whole power minus 1, which is equals to, so this is minus 1 nu naught plus nu naught. If we cancel, we will obtain half n delta nu plus half n delta nu, which is equals to n delta nu whole power minus 1. So which is equals to, if n is the integer, so here we have 1 by delta nu. That is the inverse of the bandwidth. So delta nu is nothing but bandwidth. So here fluctuation frequency, here time frequency. Here time frequency, which is equals to 1 by delta nu. So the inverse of the bandwidth of the laser beam, where the laser is oscillating below threshold. So various modes are largely uncorrelated as a result of the absence of correlation between various spontaneously emitting sources. So here these fluctuations become much less on passing above. So passing above threshold, but the different modes still remain essentially uncorrelated, and the output intensity fluctuates with time. So from equation number 3, it follows that average intensity is given by. So this is the average intensity IAV, which is equals to K sigma n mod an whole square. So here from the equation 3. So from the equation 3, here we will obtain the intensity. So here this is the average intensity 6. So if we assume all modes to have the same amplitude A naught. So if we assume all the modes will have the same amplitude, so then we can write intensity average equals to n plus 1 into k A naught square. So let us consider case when all modes are locked in phase. Here we have considered same amplitude. All modes have the same amplitude. Now another condition: if all the modes are locked in a phase, that is phi n is equals to phi naught. So if we assume for simplicity that the amplitudes are also equal, that means all modes are in locked and amplitudes also equal. So resultant laser output amplitude will be given by E z of t equals to a naught e power I phi naught sigma n equals to minus n by 2 to n by 2 exponential minus 2 pi I nu n t minus z by c, which is equals to a naught e power I phi naught exponential minus 2 pi I nu naught t minus z by c into sine pi delta nu n plus 1 t minus z by c by sine pi delta nu t minus z by c. So which is the equation number 8. So output laser intensity is proportional to E z of z comma t whole square. So which would be I of t equals to k E naught square sine 2 pi n plus 1 into delta nu by 2 t minus z by c by sine 2 pi delta nu by 2 into t minus z by c whole square, which is the equation number 9. So here the variation of the intensity is given by this equation number 9. It is as a function of time at a fixed point, or as a function of z at a fixed time, which is shown in figure 6.11. Here this is the pictorial difference. So here the time variation of the output intensity of a mode locked laser. So pulse repetition rate is 1 by delta by nu, which is equals to 2d by c. So here time taken for a complete round trip of the optical cavity, and the pulse width is given by 1 by delta nu. That means the inverse of the bandwidth of the gain medium. So here the variation of the intensity can be seen in the 6.11 as a function of time at a fixed point. So as can be seen from the figure, the output is now a regular sequence of well-defined pulses. So here we can observe the regular sequence of the well-defined functions. So here so output consists of a sequence of pulses which are separated by a time interval 1 by delta nu equals to 2d by c. So this is exactly the time taken to complete a round trip in the resonator. So here we can observe for a round trip, it is the time interval 1 by delta nu equals to 2d by c. Hence the mode locked condition can be visualized as a pulse which is traveling back and forth in the laser cavity and which loses a part of its energy through the output mirror in every round trip. That means whenever we can observe the light is traveling back and forth in the laser cavity, and which some of the light can be, some of the energy can be lost throughout the output mirror in every round trip. Okay? For each and every round trip, we can observe a loss which can be obtained through the mirror, one of the mirror. So that is the loss. So from equation 9, it also follows that duration of the pulse is approximately given by Tp, which is approximately given by 1 by n into delta nu. So which is equal to 1 by n nu, delta nu. That is inverse of the bandwidth. So here duration of the pulse, which is inverse of the bandwidth of the atomic length. So thus the larger oscillating bandwidth of the laser medium, smaller will be the pulse width. So whenever we have the larger oscillating bandwidth of the laser medium, smaller will be the pulse width. So for a typical gas lasers, that means if you see the pulse width can be obtained at about 1 nanoseconds. So since the oscillating bandwidth of the solid state lasers, if we consider the solid state lasers, the oscillating bandwidths of those solid state lasers are much larger. So one can indeed obtain pulses as short as 1 picoseconds or even smaller. So such pulses are referred to as ultra short pulses and find widespread applications in the study of ultra fast phenomena in physics, chemistry and biology. So which was done by Shapiro in 1977. So from 9, the third point is, so one can obtain the peak intensity of the output pulses as I peak represents the peak intensity which is equals to n plus 1 whole square Ka naught square. So that means already average intensity we have n plus 1 into Ka naught square. That means here the peak intensity which is n plus 1 times the average intensity. So that's for the solid state lasers having 10 power 3 to 10 power 4 modes of oscillation. So the peak power enhancement obtained due to the mode locking is very large. So we will obtain the peak power is enhanced due to the mode locking is the output obtained is very large. So various techniques have evolved. Let us see some of the techniques evolved for locking together the various modes. So if you consider an example, if we introduce a device into the resonator cavity. So if we introduce a device into the resonator cavity, so which modulates periodically either the loss or refractive index of the cavity. So whenever we are introducing a device into the resonator cavity, the device modulates periodically loss or refractive index. So such a technique is referred to as active mode locking. So since the modulating device is run by a source other than the laser. So in order to understand how, for example, a loss modulator placed inside the resonator can lock the various modes in phase. Let us assume losses is modulated at a frequency delta nu, so which is the intermodal spacing. So as soon as the laser is switched on, so whenever we are placing a device into the resonator cavity and if you switch it on, so the mode that lies nearest to the line center, that means at frequency nu naught, would start oscillating first. So we can observe the mode which is near to the center which oscillate first. So since the loss is modulated at the frequency delta nu, the amplitude of the mode would also oscillate at a frequency delta nu. So and finally the resultant will be given by A naught plus A1 cos 2 pi delta nu t cos 2 pi nu naught t, which is equals to A naught cos 2 pi nu t plus half A1 cos 2 pi nu naught plus delta nu into t plus half A1 cos 2 pi nu naught minus delta nu into t, which is the equation 12. So thus this modulated central mode is superposition of oscillating modes at a frequencies nu naught, mu naught plus delta nu, mu naught minus delta nu. That means so here the modulated central mode, which is a superposition of oscillating modes. Which, what are the frequencies? Mu naught plus delta nu, and mu naught minus delta nu. So oscillating field at a frequency is mu naught plus delta nu, mu naught minus delta nu. So these two forces the modes corresponding to these frequencies into oscillation. Thus, these mu modes have a perfect phase relationship with the mode at mu naught. So, the amplitude of these mu modes are also modulated at the frequency delta nu. They create additional frequencies mu naught minus 2 delta nu, mu naught plus 2 delta nu, in addition to those already present. Already we have some of the modes, and additionally we will obtain these frequencies, these modes with the frequencies. So all the modes are forced into oscillation in a definite phase, and this leads to the mode locking. So mode locking can also be obtained by using saturable observers. So this is about mode locking. So within a short duration of time, we will obtain high peak powers. Okay, thank you, children.